Okay, I forgot to record. So now, okay, anyway. So now we kind of, let's look at K-armed bandit problem. Assume that you have a K different these machines. And when we say K different options and actions means that choose different machine to make an action, just pull down, right? Pull the arm. Then if we repeatedly face this choice, but the thing is that you don't know those distribution. So after each choice, we receive a numerical reward, choose from a stationary probability, right? Stationary probability. So, okay. Can you hear my sound clearly? So in the Zoom meeting, can you hear me? Anyone? Okay, yes. Clear? Yeah, okay, great. Okay, so here I highlight this stationary probability. Actually, there's also many times in real world, actually it's non-stationary cases. But in the current setting, we just learn about the stationary probability. So our objective is to maximize the expected total reward over some time period, for example, like 1,000 times. So if you look at here, this diagram, and yeah, so you have like A, B, C, D, E, F. You have these 6 options or bandit, like 6 arms. Then you need to choose which one is the best option for you to run. So if you look at, actually, you just need to check the average, the expected, right? So if you carefully look at each distribution, obviously the C has the highest expectation, because if you just look at the x-axis is the reward, then this is the probability. So if it's larger, if from this part, then this becomes larger. From this direction, it becomes smaller. Obviously, you just need to get the average expectation. So in the center, the average move as large as possible to the right direction, right? So which is this one. So among all these 6 options, this C has the highest expectation. All others are smaller, right? Yeah, smaller, and the F is positive. Others are all negative. So this C is the best option for us. Okay, but in reality, the thing is that if you know this probability distribution, it's okay. But actually, most of the time, in real world, we don't know. Actually, you don't know. Nature way is that you just try, or you can randomly try. You can try from the beginning, 1, 2, 3, 4, 5. And each time it will give you a random number, random reward based on this distribution, right? Sometimes it comes here, sometimes it comes here, sometimes it's here, right? But if you keep trying different of them, then eventually you will find that this C will give you much higher chance to get higher reward, because its distribution is, the expectation of this distribution is higher. But so before jumping to the solution, we can play again here. So let me just click. You will see. So we have this again. So this is like a simulation, okay? So we have this. I assume that we have these 3 arms. Then you have we have 10 times to click. So each time it will give you a reward. Okay, we only have 10 times. Okay, so press 1 button to get started. We will pause the game after 10 button pressing actions. So now after 10 times, you will decide which one is the best option for you. So most of the time we just start from the beginning. You click is 4, 1, 4. So maybe next time when we choose, we only choose from the first and third one, right? We try to 4 again, 4 again. Oh, both seems good. They are. Oh, this one is higher. So now so which one would you choose? Maybe the third one. Third one has some chance get the higher reward, right? So it gives the answer. This one, and you can play again to try. So each time you will generate different distribution, and you will get the different. But sometimes you will get the wrong answer because there's a tricky part there. So you may select the wrong, less optimal, less the action or the one that it has less rewards. You can try many times and you will see. Sometimes you got the better choice. Sometimes it's less better choice. Okay, worse choice. Then in real world, actually there are many applications related to MAB. So we can use MAB to solve different problems and or design different like services. For example, the first one is drug experimental treatment. So most of the time, so like a new peers or new medicine, how doctors need to decide whether this medicine is effective or not. So for this kind of problem, actually we can design. For example, we have assume that we have 4 medicines here, 4 peers, 4 type of peers. We have 4 arms. So they have each medicine has different ingredients, slightly different, but they may have all have effect, but only one has the highest cure rate. Okay. Then for patient T, prescribed treatment AT belongs to these 4 arms, right? The action it can choose each one, so you can only choose one to take. So the patient T, this T is like time step. So if you have 1,000 patients, it means that you will try 1,000 times, right? I mean, if you have a unlimited patient or enough patient, you have a statistic value to see which one is the best. Then observe the reward RT. Observe the reward RT belongs to 0 or 1. So it's like between 0 to 1. E is here, 0 is not. So the reward should be between. So I mean, this reward can be decided by the doctor, right? A doctor may decide eventually after checking whether the disease is cured or not, or like partially cured. It can be a 0.5 or 0.7. Then our goal is to maximize the total number of patients here. So we need to find which arm is the best, which peer is the best option for a particular disease, and the most patient got cured. Okay, this is one motivation. So I mean, so traditionally in medical area or pharmaceutical area, so they need to do it in real patient, right? They need to do it in real patient. They call it some blind test or something. Yeah. So it's like there is a they have this so-called comforting peers. So it's like it has no any effect. Another peer has effect. So just to remove some like psychological effects to the patient. Okay. Then the next application can be recommendation systems, like online advertisement, movie suggestion. So it's like when you browse a website, then you have many advertisements. Which advertisement is interested to you? You are willing to click. You want to check those advertisements. And the movie suggestion. So for the movie suggestion, it's like this online streaming platform. They have a lot of this kind of they want to get revenue higher. So you are willing to pay to watch their movies, you subscribe. For example, Netflix, right? A lot of in Korea, a lot of people subscribe Netflix. That they watch a lot of movies in Netflix. So, for example, you have a K movies. So it's like K arms, right? For visitor T, it's a time step. So you have a lot of subscribers, or recommend movie. The movie can belong to K movies from 1 to K. So this is the action. And so each visitor, each subscriber just choose one movie. After watching the movie, the visitor subscriber gives a rating for this movie. So this kind of reward, the rating from 1 to 5, 5 levels movie. Then the purpose is that to maximize the total average rating for recommendation. Means that when a subscriber or visitor watch a particular movie, so it has a higher expectation or like satisfaction for the recommended movie, right? Then obviously, if the subscribers have a higher satisfaction for the movie they are watching, obviously they are more willing to continuously subscribe the service, right? Then their revenue will be improved. So the platform, the Netflix platform and any other platform, they can do this online or based on the data. And maybe you are not noticed, maybe they in their back end, they already collect the data, they did this checking and do the better, improve their service. Okay, it's all about the data, right? So because if you watch their movie, you already give the data to them. They can just improve their services. Actually, the TikTok, I guess they do it more aggressively. Actually, they collect a lot of data for this kind of recommendation system. Not only some rating, actually a lot of personal information, and also the environment information for like different subscriber. Based on all those information, they can give you a more satisfied short movies or short video clips. Yeah. And so now we are defining this MAB problem. So we have a K-arm bandit. So each of the K action has the expected or mean reward, given that the action is selected. So we call this expected reward as the value of that action. So now, from now on, we just call the value of the action, okay? So we denote the action select on the time step T as AT, okay? A little bit small, AT. AT, and the corresponding reward as RT. So the action is A, capital A, reward is capital R, RT, so give the time step. The expected value of the action A can be defined as, so this is the expectation, conditional probability expectation, right? So based on the condition, you choose action A as a time step T, you get a reward RT. Then we define, so whenever you see this dot above the equal sign, means that we define, okay? We define this value to here. Q star A is the expected value of the action A. The estimated value of action A at time step T as QTA. So actually you see here the expected value and estimated value. Then they are different. So the expected value is the value we try to get close, is the true expected value of this random variable distribution. But this estimated value of A is QTA, is the value we received at each time step. So actually we don't know the true the distribution, right? So it's like this is a practical value, this is a true value. So our purpose is that our goal is to let QTA get closer to small q star A. Okay, so this one is the fixed. value because it's expected value. This one is changing every time, because every step is changing. Okay, so the purpose is we just want to get each time step by step the QTA to get closer to the Q star A, right? The small Q star A, that's the capital Q TA. So this is the Q star A means that this is fixed, not the time vary. And yeah. So for solving this kind of process, MAB problem, we design so-called, there are multiple method approaches. So most of the time we just call it action value method. In the last lecture, we introduced a general method. We call it the if you look at the value-based method. So here actually this is one of the value-based method, but we combine it with action actually because we only particularly consider the action value, right? This action value, then we call it action value method. So the simplest way is that we can just compute the mean value of the reward received after each action. So how you can calculate the QTA? QTA is defined as the sum of rewards when A taken prior to T. So before T time, all the sum all the reward and divided by the time step, how many times we choose A. So if you write in the here, you can write in the mathematically, okay? And a little bit tricky part is here, okay? In the textbook, they use this one symbol to represent, it's like a binary indicator whether an action is chosen or not, okay? You see, this is a binary, whether it's 0 or 1. Actually, they use 1. If the action is chosen, AI equals A. So the particular action is chosen is 1. Otherwise, it becomes 0. The rationale is that, okay, because you have multiple arms, right? K arms. So when you calculate this, there could be some arm is not selected, only select the one particular arm. And also you need to count how many times this arm, this action is selected. So it's like counting, okay? Then actually, if you just look at here, it's simple, just sum the rewards and the number of times A was chosen, was taken. Yeah, you can calculate in this way. So there's an explanation where it's just binary, right? Binary value. If the action is chosen, it's 1. If the action is not chosen, then it's 0. So there's also denominator. If the case denominator is 0 because at the beginning stage, then we just define it as a 0. From mathematically, it should be complete, right? As the denominator goes infinity, so as the number, the times we choose this action goes to infinity, as many as possible, as many as we can have, then the QTA obviously will converge to the Q star A. So statistically, right? Because we have a distribution, and if you run it enough, it will gradually, the average will gradually close to the expectation, the average value of the target distribution. Then we call this method the sample average method. Okay, I mean, yeah, just statistics way to calculate this. So any questions? Okay, so now we move to then the problem is that, so you see here, the problem is that here the sum rewards when A taken. So it means that you need to, for example, you have a K actions. So you need to actually memorize every action's history rewards and record the number it has been chosen, right? It means you need to save all those data. when calculate the value. So in that case, actually, it's not memory efficiency, and it's not good to implement. You don't need to actually when you write a program, if you save all those data, it kind of occupies a lot of. If you consider the K is very large, then you need to occupy a lot of memory and cost a lot of resources. So there's a incremental implementation. So we can a little bit rewrite this equation. So on a single action, let Qn denote the estimate of this action value after it has been selected n minus 1 time. So we define this Qn. So Qn is, so we just consider one action, a particular action, Qn equals, so it's just the history reward divided by how many times it has been, just average, right? Then define the Qn. So the value, the action value is Qn plus 1, then equals, so this is average, right? So this is just exactly previous the equation. Then you can divide them to the Rn plus n minus 1. So previously is I from 1 to n, now it's sum to 1 to n minus 1 and Ri. So it's like just extract the current reward and the history. Now we can do a little bit tricky. So we times the n minus 1 times 1 over n minus 1. So it's like just equals 1. Actually, it's just same. And then this part become, if you look at the Qn, the definition of Qn, this part is just Qn, right? Because n minus 1 is just average of the previous state, which is this one, right? So if you Q n minus 1, then the n minus 1, right? This, which is previous one, which is Qn. Now in this case, then you rearrange order. So yeah, n times Qn minus Qn, rearrange. So but let's move out the Qn and times n, which is Qn plus 1 divided by n times Rn minus Qn. So eventually, actually, in the implementation, we can do it this way. You can calculate Qn plus 1 equals Qn plus n minus n times Rn minus Qn. What it says here is that a new estimate equals the old estimate plus step size times target minus old estimate. Okay, this is what is the incremental implementation. But actually, this, even though the derivation is simple, but actually it has from computer science point of view, it has very useful information here, because this step size, later on when we talk about the step size, as you can see here, the step size, when we talk about step size from original point of view, the step size is 1 divided by n, right? So n is changing. So every time this step size is changing, and when you reach to like large enough, it becomes very small, tiny, like a number, right? Later on, when we deal with different kind of scenario, we can vary the step size. Instead of using this 1 over n, we use like some fixed value for this step size later, okay? But actually, if you fix the step size value from this point of view, it doesn't make sense. But from other scenarios, actually it can increase some performance. So we'll look at it later. So this incremental implementation, actually you can find this similar pattern in other area, okay? In other like optimal control, some estimation theory, they have all those areas, they have a similar, this kind of deviation for the new estimate of some system status. Yeah. So let's look at an example. Okay. We have a list of the reward from the action A until step 6. So the reward here, like we have this reward, yeah, 6 reward. Now based on the equation, so it actually just calculate the average, right? It's simple. Just sum them all the rewards divided by the time step equals 4.8. So this is the time step 6. For the next time step 7, we can just use this incremental implementation. Then so the next Q7A equals Q6A plus 1/7, and use the Q6A, use the latest reward minus the previous reward, action reward, which is 4.8. Okay. Now in this way you can calculate the latest reward, which is 5.1 of the value of the action, which is 5.1. Then in this case, from the programming point of view, it's not that difficult to save all those data. Each time, just do it like recursively or gradually to increase the number. Eventually, you can reach the number you want to get, the expectation value, right? No question, right? It's not that difficult. So now, so far, we have been done the value calculation, the action value. How we can calculate the action value? After calculating the action value, then we need to make the decision to choose which action to take. So actually the simplest action selection rule is that just select the one with the highest estimated value. We call it greedy action selection method. We use this argmax to represent this kind of method. We call it, so the argmax means argument maximization, maximize. So with this argument, it can maximize this value, this function, okay? So because A is one of the arguments, right? So this function may have multiple arguments, but A is one of them. But in this case, just the QTA only has one argument, okay? And with this argument, this QTA will be the maximum. Then we define this maximum value. The action will be AT. So actually, you need to remember this definition. When we do the argmax QTA, the return value is the action, okay, which should be a particular A, not the value. So you know the action A for which the expression that follows is maximized. So yeah, this is the definition of argmax. So the argmax, I guess some of you already see this a lot in other like learning, deep learning, machine learning stuff. So sometimes we write the optimization, the process with this argmax. So we need to maximize some function by choosing a particular or a group of arguments. So actually, this is the natural way, right? You just select the highest value, then it will be the best value. But the thing is, there's actually some issue with this greedy action selection, because it simply exploits the current knowledge to maximize the immediate reward. No exploration at all. So it's like just select for example, it did not explore the environment, other possible options, right? And it's also possible that when we do the selection, it becomes suboptimal and far less optimal. So as we play the game, this one, the one we played, right? So you choose either one at the beginning, you just select one by one, and you see the return value. Then you make the next decision and continuously click. But always you will choose the highest, the greedy, highest value. But sometimes the highest value may cheat you, may like fool you that even though you got the highest value, but actually that's not the best action you need to take. For that case, we can add a small probability, epsilon, to do some exploration to avoid this situation, okay? That is, we select randomly among all the action occasionally. Occasionally means that the small probability. Then after this small probability, then we select randomly based on the equal random, okay? So this method is called E-greedy action selection. So any questions about this E-greedy action? As I mentioned here, select randomly among all the action occasionally. Occasional means that follows this probability, a small probability. Epsilon, okay? So then we have this like a question. If we use this method, action selection method, epsilon greedy, for the case of two actions and epsilon equals 0.5, what is the probability that the greedy action is selected? What is the probability? Anyone? You can raise your hand to share your opinion. How to calculate? You don't, yeah. Including online. Yeah. Anyone you want to share? No one? Okay. Yeah. So okay. So actually the process is simple, right? It's not that difficult. So you okay, we have got some answer. Closer but not correct. Some people send this 0.5. So you need to understand it's a two-step like action, two-step selection. The first one you need to decide based on the epsilon, which is 0.5. After the epsilon, you need to make the second round the decision whether this choose which action. So either randomly choose or greedy choose. So actually, so the question is, what is the probability that the greedy action is selected? Means that it need to include all the possibility of greedy action has been selected, right? So what do we? Let me annotate. Okay, so for them, so the epsilon is 0.5, right? 0.5. So assume that we have this 0.5 is at 50%, 50%, right? So means that you have a 50% to just choose the greedy action, then which is what? 0.5 plus another probability is that you are falling to the random selection, and that random selection means that so another probability is 0.5 times you have falling to the random selection, right? So the condition is 0.5 times. The next step is random selection. Random selection, because we only have two actions, is also 0.5. which is another 0.5. Now it's 0.75, okay? The probability that the greedy action is selected is 0.75. So honest, right? Any question? No question, right? It's a two-step process, right? You first one to decide to make the based on the probability of epsilon. The next step is, so this is the previous steps, then we times because we have only two actions, then randomly, they means that they have equal probability, each action. So among two actions, one of the action is a greedy action, right? Then times 0.5. So then the total probability of greedy action being selected is 0.75. Okay. So move to this. Now we just come to the algorithm, how we can implement the multi-armed bandit algorithm. Actually, the process is simple. Since we already have all those deviation, the reasoning, rationale, why we need to do this. So we just initialize the QA, which is the reward or the value of action, the step size NA, step size for a particular. So you see here NA, this should be a list, right? Because action A can be multiple action, like K action. Yeah, for 1 to K, right? A can be K actions. And so QA also, yeah, so it's like also need to be a list, okay? QA is a list, NA also list. And we just loop through. Then at the beginning for this action, we need to decide the action. At the beginning, we just need to decide the action, whether we use this arc max A, maximum A, with the select the greedy way, right? Whether we just choose the action that maximize the QA with the probability 1 minus epsilon, breaking tie randomly. If we have, so it is possible that you got two same action value. So both action has the same value, right? Then you just, in practical, we just add some very small random number to the equal action values. Then we just randomly select one. So we just breaking the tie randomly. Another probability is another possible action is that we just randomly selection based on the probability epsilon. Okay. Then after this step, then we just make a decision which action to take. We put this action to the bandit is the environment, it's a reward definition, right? Then it will return give us a reward, which the action will generate the reward. So the bandit, each machine, right? Then we can increase the step size 1 and put to here, because at this moment we already made an action, select action and receive the reward. Then we just need to calculate the current action value based on the previous value, right? So now the QA equals QA plus. So actually you see now the A become capital A. Capital A should be the like array or list. Yeah, depends on the array or list, because you need to record every action's count, right? And also every action's which action we select. And the QA plus N minus just this equation is just the incremental implementation. Then we can just update the QA. Next time we loop again and again, loop not forever, maybe just 10,000 times. Then you will get the very reasonable value for each action, then you will see which action is the best option. Okay. So this is a bandit algorithm. So let's see an example. Here, the 10 armed bandit. So ideally, we have this. We can generate from a computer program, like Python in the gym. We can build the 10 arms. Then it's equal to 10 actions. Then each arm follows the normal distribution. They have expected value. Okay. Then each one. So you will see here that which one is if you look at, you already knew this distribution, which one is the one we need to choose? Which one? Number 3, right? Obviously number 3. This is the highest, about 1.5 here, right? 1.5, number 3. This is in the program when we deal with it, then we generate this kind of distribution already. Now, if you run the those algorithms with different value of epsilon, you will see the difference, the average reward and optimal action selected percentage. So if you look at on the top, so if we just do the greedy, actually our average reward is not that good. We just kind of moving around a little bit above 1. If you give a little bit, a small epsilon, like a 0.01, or it will become better. If you give a larger, like 0.1, it become much higher. So you remember that the optima, if we know that optima is about 1.5, right? Which is Q star 3. This one is the one we need to choose. Actually, you see here, the epsilon equals 0.1, getting close to the 1.5. Still, there's some space to improve, right? Similarly, the optimal actions, selection rate or ratio, you see like also when you give the epsilon 0.1, it has a higher chance to select the optimal action. And if you just do the greedy, it may not that satisfy, actually less than 40%, maybe 35%. It's like 1/3, you get the optimal action. Actually, it's quite low, right? Then this almost 80%. So 80% you will get the optimal action. So let's play a game again. So you see from the right-hand side here, if you click. So this time a little bit different. So actually now we can show the distribution. Okay, so you have these 3 arms, then each arm has a distribution. Then we can see, if I click, you can see that each time if you refresh, each time we will generate a new distribution. So each time it will be different. So try the game for about 20 actions first to see if you can infer information about the reward distribution before pressing show distribution. So we need to click 20 times to see. So let's just try like 9, 14, 8, maybe the first one or second one. Maybe we just choose greedy, choose the 14, 12, a little bit lower, continue, 18, 13, 17, 17, 17, 14. So maybe this one, the distribution is that the mean average is about 15 or 16, right? Because we have seen 18, also 13. Maybe the average expected expectation is 15 or 16. Let's try this one. 14, 12, 6, 16, 14. The deviation seems high, right? Maybe the average is about 12. The expectation is 12, lower than the center. Let's try this one. 7, 10, 8. This is much lower, maybe 8, right? So now we see that this one should be the action we choose. So let's just keep rolling. So now let's see. So now we already kind of get some the information from the 3 arms, right? This one should be, the expectation should be around 15 or 16. This expectation should be around 12 or 13. This expectation should be around 8, 7 or 8. Then let's see if we are, like, our guessing is correct or not. Yeah, closer, right? I guess it was 15 or 16. I also guess this the 12, right? This one I guess the 7 or 8, close to this. Now you will see the statistics we did. How many times we pressed? We pressed 11 times, and 18 times, 12 times. Now we got the reward, the accumulated reward return or value of action. Then we get the average, right? Based on those information, we just guess. So we just make the decision in the middle one. The center one is the one has the highest expectation, right? Okay, this is how this algorithm works. Okay, this is 3 arms. You have like 100 arms or 1,000 arms. You do this process, and you will get the one. You will gradually get close to the one which is the best option for you, action for you. Okay. Any questions? Hyperparameter, you mean? Yeah. Yeah. You mean the decision? So your question is how to select this epsilon value, right? Yeah, this is the hyperparameter. You can adjust. You can specify. I mean, because in practical, you don't know what is the best value for this epsilon. You need to run. Maybe you vary the epsilon value, right, from larger to smaller. Then you will compare the performance. Which one is the best option? Okay, any other questions? And online, so if for students online, if you want to ask question, you can, there's some button to raise your hand, something, right? I don't remember if there's a button. You can put some reaction or something. If you want to raise your hand, if you are reluctant to say something, you can just send those interaction item. As I remember, there's you can send some reaction item, right? For example, what? Okay. Recognize hand gesture. Reaction, right? There's some interaction way. You can just raise your hand or something. Then you can ask a question, or you can also type your question in the chatting the box that I can see it. Okay, so we move to the next. So as we mentioned previously, when we deal with all those process, we're dealing with the stationary probability. It means that each arm, each action behind those actions, the probability is stationary, is fixed, it's let's say does not time vary, does not change based on the time. So if it's non-stationary, means that each time step that probability distribution is shift or changed a little bit, or I don't know, anything can happen. So we call those kind of cases are non-stationary. Okay. Often, most of the time, those kind of RL problems are non-stationary. In that case, we need to deal. Actually, there are some methods. One method is to use a constant step size parameter alpha. As I mentioned, this alpha. So even though when we derive this alpha, is the step size, or it's 1 over n, right? N is time vary, so it's when you try the large enough the number of steps or times, then it become very small. But for the non-stationary, actually you can fix this alpha with a particular number. So this alpha should be between 0 and 1. Then a weighted average or past reward and the initial estimate Q1. So actually, if you extend this, formula one more time. So a little bit small, let me enlarge. So we fix this alpha. Now we can extend like this formula, okay? Qn plus alpha times Rn minus Qn. So you just split it and reorganize the position. It becomes 1 minus alpha Qn, because Qn is still here, and alpha n. Then the 1 minus alpha times Qn, then Qn can be is the previous state value, action value, right? Then you can just use the previous action value, alpha times Rn plus 1 minus. So it's like this format, then move to here again, because this Qn is the previous. Now we just change the subscript to n minus 1, okay? Because we already derived this value equals Qn minus n plus 1. Yeah. So then we can just continue doing this process. Eventually, actually, we can divide. So continuously doing this process, you will get the like squared, right? Then plus a lot of information. Then we can do the summation. Reorganize the value. Okay. So this 1 minus alpha n Q1. So you see that eventually, actually, this part we cannot do the summation. So we just move this part to the front, and the remaining part, if you look at the pattern here, it's like 1 minus alpha times alpha, 1 minus alpha squared alpha, 1 minus alpha n minus 1 alpha. So actually, they all have this value with n, right? The n. Then we can just put them here together. Then R is the Rn minus 1, Rn minus 2 until R1. So we can put Ri here. So the index is that I equals 1 to n. Can shorten this equation. So eventually it become the weighted average of past reward and the initial estimate of Q1. The meaning of this constant fixed the alpha. If we fix the alpha, okay, because alpha does not change anymore. If you look at here, so this is the Q1. Q1 is the first value, and plus the weighted. So if you just, this is the reward, right? Each step is the reward. Then all these values are coefficients. It's just a particular value. We can just say it's a weighted reward, and then we just accumulate them together. Okay. Another method is to vary step size parameter from step to step. So instead of using, as I mentioned again, so previously, so alpha initially when we derive this equation is 1 over n. Now we can vary this alpha based on another process. So actually, this non-stationary MAB is still active research topic. There are many methods to deal with non-stationary methods and for different kind of scenario. Okay, you can read the textbook or read other document if you are interested. Okay, any questions? So if you don't have a question, let's take a break and come back again, okay? Okay, for the online student, let's take a break. Yeah. Okay, so let's continue our lecture. Now, a short summary for what we have been learned. What have been learned, yeah, right. So we have learned what is the MAB problem, multi-arm bandit problem, and what are methods we can solve the problem. So sample average method or action is one of the action value methods, right? Then after this method, when we need to make the action selection with a greedy action selection or epsilon greedy action selection, the method to deal with non-stationary scenario. Okay, since we already everyone has been going through this MAB problem. If you go back to the applications, so now you consider means that so if you look at we have K arm for this treatment, so means that from the computer point of view, computer science point of view, each medicine has a distribution, right? The purpose is to get closer to the distribution and to know which one has a higher expectation. Similarly, this recommendation system movies, each movie has this observation reward, the rating has a distribution. Then the thing is for the visitors, the best movie, the higher rating, we should recommend to the visitor. Okay. Now we move to another topic, which is finite Markov decision processes. In short, finite MDP. Here, when we talk about finite, it means that the status is finite set. Okay. So before we go into this finite MDP, we first need to have some setting. Need to have these settings. So as we did before, we have this environment. Then the thing is the sets of states, action, and reward are all have a finite state of elements. Okay, so instead of infinite, so all these SAR they have finite number of elements. Then the random variable RS have a well-defined discrete probability distribution, only depend on preceding state and action because it's a Markov decision process, right? So the current state only depends on the previous state, does not depend on the history or the history, right? Now, before dealing with the finite MDP, we need to know some dynamics of a finite MDP. So actually, there's a lot of this kind of probabilities. For particular value of this random variable S prime belongs to S, R belongs to R, small r belongs to capital R, there is a probability of those values occurring at time t. So we are defining this probability from one state with an action, move to another next state with a reward. So this is like a transition. Okay, this is the probability. Then how we define this? When we just similar. we select a particular, we are in a particular state, we are in action. Then we move to the next state, s small s prime with a reward. And we define this probability as this p. Actually, this p, we define it as a probability. Since the p specifies the probability distribution for each choice of s and a, so it's naturally we can see that if you just include every possibility, every cases, then the probability equals 1. You just do the sum all the states, sum all the rewards, s prime they should be equals 1, right? Because based on the probability theory, you will see that because it includes everything, even though it's under the condition. The next three dynamics are one is the state transition probability, means that probabilities from one state to another state. So we use this p, small p s prime under the condition s and a, means that the current state and the current with an action, with this information condition, we move to the next state, the probability of move to the next state, because we define, which is so the probability of this one, right? Then how to calculate this probability? We just summation all the rewards, right? Summation of all the just based on the previous one. We just need to summation all the rewards and for a particular state. Yeah, we can calculate in this way. Next one is the expected reward for state action pairs. State here, expected reward for state action pairs. State action, the reward of this state action is defined as the expectation of a conditional probability under this condition, the state with S and action with A, and then we can get this reward. So calculate the expectation. Now, if you calculate this expectation, it will be calculated in this way. So if you look at how to calculate the expectation, EX equals all possible X, and X times P, X equals X. So which is what we are writing here. The R is this RT, and we just, because we are using this sum symbol. If it's a continuous random variable, we need to use integral, okay, integrate. So now we just use the summation, sum all the R and sum all the, so this probability P is the sum all the states. So this one also from the previous one, right? The sum all the states, because R is the one we don't with the particular R, right? Okay, this is how you can calculate. Then the next one, expected reward for state action, next state, triples, state action, next state triples. So you just, take a look how it's written. Actually, we don't use that much. But maybe this one we may use sometimes. Then later two, we don't use that much. Sometimes we just slightly use. But this one need to remember, okay? Just simple, because it just include all the possibility of S prime and R equals 1. Later on, we need to use this condition to calculate some value. Discounted reward. So we learned in the last lecture, what is the definition of discounted reward? So we have this return. We use TT. It defined as all the, if there's no discount, we just accumulate all the rewards we receive along the step. Then discounted reward, we just add the gamma and gamma squared. So in short, we can just write in the gamma to the power k times RT plus k plus 1. So yeah. Returns at excessive time step are related to each other. If you rewrite this discounted return, so GT equals R So just exactly the same. And if you extract the gamma, you will see the part inside of the bracket is just the last steps discounted return, right? We can just simply write the gamma g plus 1. So the current return, the reward plus the discounted previous step return, right? The previous step return, let's say in this way. So now we are defining the state value function. So in the finite MDP, actually we have two types of function. One is a state value function, another one is action value function. The action value function, we saw it in the k-armed bandit problem, right? Action value means that we need to calculate the value of action. Then now here we have another called the state value function. We need to calculate the value of state. The value function of a state as under policy pi. The policy pi is the way or the strategy to decide the action, right? Denoted, we use the v pi s to denote this state value function. So how we define it? We define this state value function as the expected return when starting in s and following in pi thereafter. So it is expected return. It's it's a expectation. Okay. How we can calculate? We define in this way, right? The GT is the previous return, accumulated reward or return GT. Then based on the state under the condition state, we got this reward return. Then we assign this value, the expectation of this value to the v pi s. So remember, this is the state value function, means that we are defining the value of state. So from the definition here, we can see that, so this value is related to the state. S is the state. The v pi is the value based on the pi, the policy pi, then equals. So how we define it is that under the condition of the state, the current state, we have a particular state. Then we have the reward, accumulated reward or return. Then we calculate the expectation. What is the expected return for a particular state? Then we define it as a v pi s. So it's related to state and the reward, right? State and reward. That's why we call it state value function. How we calculate it? So because GT is just simply this one we calculated in the previous step, right? We just discounted the reward, discounted the accumulated reward, which is here. Then we call this function v pi as a state value function. So this is the first definition, state value function. Okay. Now next definition is the action value function. Similarly, action value function is related to action, right? Means the value of an action. So the function is related to the action. We define this, we use q, small q pi sa to define the action value function. So here it involves a state. What is the definition of the q pi sa? It is the expected return starting from S, taking action A, and thereafter following the policy. So should be on a state and taking action, then the expected return for this action. So similarly, we use this Q pi SA is defined as the expectation GT. So similar to the previous definition, the difference is that we add an action with a state with an action, then the return. So similarly, we can extend it how to write this. So yeah. Oh. If we use this action value function to calculate the value of action, we also call it Monte Carlo method. Okay, it's one of the Monte Carlo method, averaging over many random samples of actual return. So we will learn this later, how it can be used in our RL problems. Now we come to the famous Bayes-Mann equation. Okay, so as you remembered that, as I mentioned, as I recapped, so we have a grid word. The grid word, each of them has a value. So how we can get those values is based on the Bayes-Mann equation. Okay, somehow I don't know how this person find this form of the equation. Then it has a very meaningful way to calculate. So the state value function can be extended to a recursive version. So this is the state value function, right? We have the state, and this is the value function, v pi following the policy equals this, then this GT is remember, is a return, right? For the online student, let me use the pointer. So GT is a return, then we can rewrite it in a recursive way. RT plus 1 plus gamma GT plus 1 under the condition of ST equals S. Now from this part to next part is there's a long derivation process from here to here. And then eventually, if you look at here, E pi GT plus 1 under the condition ST plus 1, this part actually is this part. So this is the next step, T plus 1, right? Just the time step different. Others are the same. Then we can just write V pi to here. So eventually this become a recursive process. V pi S equals this is the policy, right? Pi is the policy. We do based on some state, we make an action with summation of them, all the policy. Then remember here, when you look familiar, what is this? This part from here to here, this part. What is the value of it? So it's the condition probability of MDP, finite MDP dynamics, right? You have the current state, you make an action, you move to the next state with a reward. If you do the summation of all the S prime R equals 1, right? This part equals 1. Okay, actually, this part equals 1. So now, then the remaining is R plus gamma. So R is a reward, gamma is a discount rate, and V pi S prime is the previous, next state, right? Means that we can calculate the current, the value of state based on the next state. This is the meaning of the Bayes-Mann equation. So I don't know if you want to go through this derivation process. So actually, I put in the appendix, and let's go to see how you can get it. Okay, appendix at the end, you can click, then you will jump to the end. Okay, deriving Bellman equation. How you can. So the problem is how you get here to here. You just extract all those stuff and with this stuff. So let me just briefly go through how it works. Okay. So the problem is that the jumping from here to here, there's many steps to move to here. Now, start from here, you will see how it works. So V pi s is defined as the expectation of this GT under the condition ST equals S. Then we can rewrite the GT as this next state with the reward plus the discounted return under the condition. So based on the linearity of the expectation, this is a linearity. So this is conditional property. Under the condition Y, there's AX plus BZ, we can rewrite as A expectation X under the condition Y plus B expectation Z under the condition Y. This is the linearity of the. Now, similarly, we can rewrite this part into two parts, right? R plus 1 ST equals S, and gamma expectation G plus 1 under ST equals S. So you just separate them, right? This RT1 under this condition, gamma GT1 under this condition. Now we have two parts. Now we need to deal with them separately. The first part, the first item is RT plus 1 ST equals S. We can, based on the definition of the expectation, as shown here, now we can just write some RP, this is a probability, right? Then condition probability under the S condition with R. You have this, then you calculate this one, right? Then the thing is how we can calculate this conditional probability to here. We can extend this condition probability into marginal distribution. For example, here we have under condition S with this R. Then we can just add S prime and A with the summation. Sum all the S prime, sum all the A. So they are equal. There's no difference because this is marginal distribution, right? Now we can rewrite. So how we can switch this, transform this part to another form. We use this transformation. If you have this PAB under the condition C, if you read this process, eventually you can get this PA under the BC, PB under the condition C. So we can do this transformation. So yeah, with this, let me just do the first one. Then others I will, you can check by yourself. Okay. So our target, so we have this formula, this probability. The target is to reach this form. So for this, right, I just moved to here. Now from this probability, we can get to this part. How we can get? So because this P is just the policy, so we can just rewrite as the pi. There's no, so the problem is how to derive the property from here to here. And what we do is that I write from this P S prime R A S. So based on this process, actually we can rewrite or you want to know the detailed process, we can write P S R A S divided by P S. Now we can times P, what is that? AS, right? AS, P, A, S. Now, because they are just redundant, just one, and then we switch PS and PAS, you will see the PS prime. This is R, A, S, P, A, S times P, A, S, and this is PS. So now this part become this part, right? Then this part become this part, right? So this is how it comes. Now, once you done this process, you just move. So now we are just reaching to this format of this probability, and you move this part back to the original this expectation, which is to here. Then you can get this form. Okay, this is how you derive this process. Okay, let me clean. Do I need to save? Save. Okay. So move to next one. The second item, I don't go to detail. You can check by yourself. A little bit complicated, but mostly similar. We still you need to use this transformation process. And P, so it's like PG. So based on the definition of expectation, then we need to derive the PGS. Then still we extend this PG on the condition S to add S prime R A G. So the original is just G. We add S prime R A. So sum all those possibilities. Then you can do the transformation and transformation. So actually this one, the second line, this is redundant. They are the same. I guess the original purpose is this pi should be P. Yeah. So the second, these two items are the same. So actually this one should be P, and then transfer to pi. So eventually to this form. Now we just merge the two parts. What do we see here? Okay, we just merge the two parts. As you can see, the first part is here, the second part is here. The merge, there is a plus gamma. So this is what we, then you can rearrange the position and order, make them together. Okay, because we have this part. So the blue rectangle highlighted part are the common part. We can move them out, right? Then means that, so we have this small r, which is here, gamma, which is here, times this part, this one, PG under the condition S prime, which is the expectation of, yeah, the definition, right? The previous that we defined is E pi G plus 1 under the S prime. It's just equal because there's a, okay, wait. In the previous, so actually there is one more. Above this, there is a G. G, okay. So in the previous page, you will see there's a G. So both sides, you add them together, will be equal to this part, expectation, okay? Based on the definition of the expectation. Now, eventually you rearrange. Now, this part is just the V pi S prime. Then this is the Bellman equation. How we get to the Bellman equation, okay? Any questions? So, okay, clear. Yeah, and then go back. Go back to the Bellman equation. Now we know how the Bellman equation is derived and how it works. So now let's use what is the meaning of the BE? So it's kind of shows us the relationship between the value of the state and the value of a successor state. Okay, the value of the state and the value of its successor state. So you see here, this is a state S, and other state, the next state will be S prime, then with 3 different actions. So the solid circle is action with the policy pi. So they have a 3, for example, this tree has 3 actions based on the policy pi. Then each action will lead to some particular states with some reward, right, and probability. And starting from the state S, the agent could take any of some set of action based on its policy. So it's what I'm telling you here. So now, if you look at here, B average all over the possibility means that it will average all over this probability. So if you want to calculate the value of state S, you need to get all the value from different actions it can have based on the policy pi. Then all this action is actually from the next state. It's like you want to get the current state, you need to use the future state information. You understand, right? So from one state, you move to the next state. The next state is actually the future state. You need to get all the information, all the future possibility, future state information. S prime represent the next state, future state. So S prime can have all, similarly, you can extend the tree, all the future states. So this is what is the Bellman equation tells us. So the value of the state must equal the value of the expected next state plus the reward expected along the way. Okay, this is one of the key equation in RL. Okay, so now let's look at this grid work. How we can use the Bellman equation to calculate a policy that give us the rewards. Now we have this setting, okay? We define this reward. If you hit the wall, -1 reward. Other actions 0. So if you move freely inside of this grid work, the reward is, the cost is 0, right? Except state A and B. So this example is from the textbook. So state A and B, the meaning is that whenever you move to state A, so if the next action for the state A, all 4 actions, it has 4 actions, right? For example, here it either can move up and down, left or right. For all 4 action will lead to A prime, and with the reward +10. So this is definition of the state A, so the special state. All 4 action will move state A to A prime with reward +10. And similarly, B is all 4 actions will move B to B prime with reward +5. So this is how the setting of this environment, what we are having. Now that we define the discount, gamma equals 0.9. Actually, we can do so we can, for each this state, we can build a BE, Bellman equation. For each state, we can build a Bellman equation, okay? Now, if you count how many states we have, 5 times 5, right? Actually, we can have 25 equations, okay? 25 equations. Then we solve the system of the linear equation. So it's 25 equations. Then we can get the variable. The solution is that the result is the value of every state. Okay, eventually, if you list 25 equations, obviously you don't want to do it by your hand, right? You can run the computer program. In Python, there's some library to run it to solve the problem. So you will get this number. And we can run some part. So any questions so far? So, okay, let's move to the next page. So how we can calculate sum of the value, okay? So initially, we just define all the value are 0. Then based on the setting reward, then we can calculate the state value from each state, right? So for example, at the beginning, do I need to, so this, can you hear my voice? Can you hear? Okay, now you can. Okay, now it works. So we have so initially we just defined the initial value for each state, which is 0. Now we just calculate based on this equation. So you see, this is the Behrman B, right? This is the B. So I just put there for us to reference. Now, this is the policy. So you see, this is a sum, right? We need to deal with each action. Okay, this is policy. Policy, the action, which is defined here. So they have an equal probability for the 4 actions, all are 0.5%. So the summation of all the actions should be 1. So the first action, then we can just calculate 0.25 times 1, which is the probability we calculated before. I said this is important, right? We will use it because this is equals to 1. Then the inside, the reward. So the first action, so we need to the first action is turn left. So we can do the clockwise, left, up, right, and down. 4 actions, right? We have 4 actions. So left, right, left, up, and right, down. So this is the left action, and this is up action, and right action, and down action. So the R here is -1 because we hit the wall. The reward is -1. Plus, this is the gamma. Gamma is the discount rate, which is 0.9 times 0 times the state, the initial state value. Okay, then which is 0. So you can continue calculate again. So up to still -1. The next is to the right hand, then it becomes 0. Then down is still 0. So eventually you can calculate the -0.5. Okay. So this is so after this calculation, this one become -0.5. So for the S1, you can calculate again. The one difference is that the up, the movement becomes 0, not the -1, because 0, because there's no wall, it can move to there. Then if you calculate, it becomes -0.25. Yeah, -25. So I mean, you can. So it's the initial. If you calculate the many times, iterate many times, eventually it will convert to the previous the value. So let's take a look at this particular A, the A state. So if you can calculate, similarly, it has 4 actions, right? Left, up, and the right and down. So we can just calculate left, the probability is 0.25 times 1. Yeah, with this one redundant, we don't need to care about it. All the reward will be 10, 10, 10, 10, because the definition of A state is that all the 4 actions will lead to state A prime with reward plus 10 and plus times 9 times 0. 0, 0, 0, 0, because the state is 0. So here the next state is 0, right? So now eventually you get 10 in the first calculation equals 10. But if you keep calculating again, like enough time, then you will gradually, this value will be changed. The state value will be changed and converted to a stable value. Okay, that's how it works. And let's also check. So next, clean. Yeah. Next. So we can, yeah, if we can just continue, it will converge to this final state. It will fix. So means that if you calculate the particular point, does not change anymore. It will all fix to this value. So if you can, we can calculate, like verify for a particular state. For example, this A state. For this A state, which is here, right? 8.8. You can, based on the BE, which is here, we can just calculate 0.5 times 1 with this reward, discount rate, times minus point, which is here, minus 1.3, because the definition is that it will jump to this state A, right? A jump to A, right? Similarly, all 4 items are the same because we already defined its behavior. Then you can just calculate them. So 4 times, because they are all the same, 4 times 0.25 times 10 minus 1.17, because there's a discount rate. Eventually you got this 8.87 because they cut the last digit, so which is 8.8, which is here. Okay. So if you can try other values. In the textbook, they ask you to check this 0.7. How you get this 0.7 value. So you can calculate by yourself. You can just check left, up, right, and down. And doing the similar, and then eventually you will get the 0.7 for this value. Okay? So yeah, this is how Bellman equation works. Okay. Yeah. So with the Bellman equation, actually you can calculate the values of the state of the given environment, and with the environment has a setting, how the reward works and what is the action is set. With that, then we can calculate all those. Then, for example, for this, if you calculate this grid word, then you then with the value of the state, you can naturally get the policy, which you just still select the highest value to be chosen, right? So for example, if you are in this state, if you are in the one, so this is the value of the state, right? If you are in this grid, then you have 2 choice, the left or right, or so which one is larger? Obviously the -1 is larger. So hit the wall, we don't want to hit the wall, right? Hit the wall, then is -1. Yeah. So we just choose the -1 because minus 1.7 is smaller than the -1. Then we just move to here. Then similarly, it has the three options, three actions to choose, 0.1 and minus 0.4. Obviously, we will choose 0.1 is higher. Then we move to here. Similarly, we will choose the highest, which is 1.5. If you are staying here, similarly, we will choose the higher 3.3. Move to here, we reach to this state. So now, actually, this is the best policy in this grid world, because our purpose is to maximize our return, accumulated rewards, right? So if you are in this state, this is the best way to move to this state and get the maximum reward. So also remember that the mouse and cheese example, so that this is the best way for the mouse to get all the maximum reward or all possible cheese it can get, okay, to reach this state. And if you are in another state from here, you can also do some, like select the highest to here, and to here, to here. So eventually, it will lead us to the highest state value which is 8.8. Okay. Once you get this value, the values of the state, then naturally the policy has generated. Now we come to the optimal policy and optimal value function. So when we talk about the optimal policies and optimal value functions, it's because that there could be many policies. For example, previously, when you calculate this grid word, the value of a state, the value of the state, how do you know whether your policy is optimal or not? So actually, there are multiple. There could be multiple policies to reach the good the value or the rewards, right? So we denote all the optimal policy by pi star. Then they share the same state value function called optimal state value function. So we use this. So the definition here is that a policy that maximum among a group of policies, the value state value function, the policy that maximize that state value function, then we call that is the optimal state value function. Okay. So this is the optimal state value function. There's also optimal action value function. If the action can maximize this is a definition, okay? Because our definition maximize the action action value function, then we call this optimal action value function. Similarly, the expected return. So based on the previous definition, we just give the maximize it, and we call it the optimal. Now, based on the Bayerman equation, actually we can a little bit change the Bayerman equation to the Bayerman optimality equation. So you see, this is the Bayerman optimality equations. Actually, it's similar to the previous one. It just because the difference is this part, right? Because here we sum all the actions, the probability of action. Now here we just need to select the policy that has the largest probability. Select the action that maximum the later part of this Bayerman equation instead of sum all the actions, the probability of actions, right? We just need to select the action and maximum the remaining part of this Bellman equation. Then we call it Bellman optimality equation for V star. There also this Bellman optimality equation for the Q star. Similarly, okay. So we put the max A we find the A prime that maximizes Q star. So similar, this is a backup diagram for the BOE, Bellman optimal equation. So the meaning is that we have this state value function. This is state value function. Then we just need to select the maximum, the action that maximize the later states. Okay. Similar here, this is the action value function. We need to select the of this here. So once you are in the state, then we just need to select the action, like the state that maximum the action, right? Okay. So now come here the grid world again. If you put those the system linear equation together, then with the BOE instead of BOE, so a little bit different, you will get a different value. So a little bit different because instead of calculate all the sum of all the possible actions, it just select a particular one to calculate. Eventually, you have this so-called optimal policy or optimal the state value. And according to this state value function, state value, then you can get this policy, right? What is the best policy at a particular state? Obviously, if you do here, because they have the same value, you can either do up and right, move up and right. Okay, this is how you can get the optimal value of the state and the optimal policy. But the thing is, so far we have been seeing how we can use the BOE. Then there are some problems with the BOE. This solution relies on at least 3 assumptions that are really true in practice. The dynamics of the environment. So, the dynamics of the MDP, finite MDP, we need to actually know it. And also the computation resources. If you have a real world problem, the BOE equations, the linear system of the equations, will be super huge, unimaginable huge. So you need to have a sufficient computing resources to calculate. And also the state need to have a Markov property, okay? So, but sometimes in the real world problems, Markov property sometimes obey, sometimes did not obey, okay? For this kind of assumptions, it's difficult to apply this BOE. So for example, if an environment has like 1,000, 10,000 states, it may take 1,000 years to solve the BOE, okay? Then we come, so there's even if we cannot have the exact result of the BOE, then we need to rely on some approximation approaches. So the people just developed a lot of approximation approaches, like heuristic search method for a tree. Because if you look at this backup program, if you write it into as a tree, actually the Bellman equation of BOE is just the tree search, right? You can write because it will become a very huge tree if you keep writing this state. Depends on how many states you have. So if you have the 25 states, the first state, the next state, third state. So there could be some tree, so a reasonable tree to search the best solution. So we can do the tree search. We can also rely on dynamic programming, so which we will take a look at later, and some other approaches. we may after midterm we may touch that part. So because especially there's a approximation method for doing those kind of tasks. Okay, summary. So we have learned the finite MDP. We focus on the Bayes equations and its optimality. And we also learned some limitations and the possible solutions. So yeah, with the Bayes equation, at least we can solve some like limited world limited environment problems. Okay, and for example, in the grid world or in the environment I introduced you in the last lecture, the gym, the environment, many gaming environment can be designed as this finite MDP. Then for that case, we can calculate the optimal solution for those kind of environments. Yeah, this is finite MDP, how it works. So far, any questions? Okay, if you don't have any question, yeah, we finish today's lecture. See you next week. Yeah, thank you. Okay, see you next week. Thank you for the online students. And you can leave the room.